Hello, everybody. In this chapter, I'm going to go through chapter 7 of the textbook. When I say, chapter 7, I mean the old edition of the textbook. So if you have old edition of the textbook, that's going to be chapter 7. By chance, if you got the new one this one is going to be chapter 8. Okay. And the chapter is talking about wavelength, frequency, energy, and then different shape of different orbitals. Before actually I start the lecture, I need to say this one. If you have old textbook, chapter 4. Chapter 4 is the stoichiometry. Chapter 5 is the gas law. Chapter 6 is the thermochemistry, and chapter 7 is the quantum mechanic chapter. It's talking about orbitals and other stuff, the one that I'm going to cover today. But with the new edition, the author of this book, what he did is split chapter 4 to 2 chapters. Now we have chapter 4 that is split to 2. This one is chapter 6. The thermochemistry now is chapter 7, and chapter 7 of the old edition is going to be chapter 8. So we're talking about new edition, and here we have the old edition. Okay. And I wrote this one just for your knowledge, and I'm pretty sure many of my students have old version. There is nothing wrong with using the old version of the book. Frankly, they are copy paste of each other. So do you need to switch to the new book? Not really. Stick to whatever you have is more than enough for the CHEM 1314 and 1515, and you don't need to spend any extra dollar to switch to a new book. Don't do it, please. Okay, so now let's go back to the chapter 7 or chapter 8 of the new edition. We're just talking about atomic structure, and we start with wavelength and frequency. We want to talk about wavelength and frequency and see what's the meaning of wavelength and frequency. So wavelength, we say here, if you have such a thing that is in y side, you'll have phases, positive, negative, and here you have time. Your wave, it can go up and down of this in a horizontal line. Let's say we started from here, it's going up and down, okay, and then it will go up and it will go down. We say the distance between two identical points. Say here maximum point and this maximum point. The distance between them, we call it wavelength. Okay. So this is gonna be wavelength. We show it by lambda, and unit for it is meter. So lambda is gonna be the wavelength, and unit for lambda, you go with meter. Okay. You need to be careful about choosing two identical points. When I started from here and I went to the maximum point, slope is positive. Okay, slope is positive, and then when we reach the maximum point, we started to change the sign of the slope, or the slope now is here is negative. So you can say, like, for example, between those two position, two point, say those are going to be identical points, so I can call them lambda, like that, because they are identical. If you figure the distance from the horizontal line is the same for both, so I can call this one lambda. This is wrong. This is not lambda. Why? Because this one is it has a slope that is positive, while here is negative. So they are not identical. When you start from here, it goes positive, you reach the maximum. Now it will switch sign, and it still is here is negative, is going down until we reach the minimum point. And now it will turn to positive. Slope is positive. Next thing that you need to know, what's the meaning of here positive and negative? Those are the signs of the wave. Okay, we say the phase here, phase or the wave is positive. There it will be negative. At the end of this chapter, you will understand the meaning of positive and negative. What does it mean when the phase is negative or positive? So for now, just keep it in your mind that the positive represent positive phase, negative here, negative phase. Next thing, if you go with like this, here, same wave. Same way, and choose one point anywhere you want, somewhere on this horizontal line. Just choose one point. I'm gonna say, for example, here. Okay, so I'm gonna go and click on this point, and now I will count number of cycles that they are passing this point in 1 second. Okay, in 1 second, I want to know how many cycles are passing this point. Here, this is not full cycle, half cycle. When you reach there, now is 1. So in 1 second, only 1 cycle past this point. We say number of cycles per second, we call them frequency. And the frequency, we show it by nu. So frequency is number of cycles per second. Okay, so number of cycles per second, and you want to figure how many cycles passing at this specific point, because it's 1. So I'm going to say, in this case, the frequency is going to be 1. So you say 1 cycle per how many second? Just 1 second. Look to the denominator, does not have any unit, it's just cycle. It says 1 cycle per second, so the unit is going to be 1 over second. 1 over second. We say the frequency is going to be 1 over second, or we show it by hertz also. So 1 over second is equal to hertz. The frequency in this case, we got it 1 cycle per second, so it's going to be 1 per second, or 1 hertz. Okay. Next, I will try to increase number of cycles that they're passing this specific point and calculate the frequency. So let's assume we have those. Okay. And now we want to figure how many cycles are passing this point. So I say 1 cycle here, and then 2 cycles, and then half. So it's going to be 2.5 cycles per second. For the red one, it will be 2.5 cycles per 1 second, or 2.5 hertz. This is going to be the frequency. So simply just count number of cycles that they are passing. This is 1 cycle until here, so you put sign there. Then that's gonna be the second cycle, and that 1/2 cycle. Okay. So it's a 2.5 cycles per 1 second. Again, we have wavelength is the distance between two identical points. Choose two identical points on any wave and measure the distance between them. That's going to be wavelength. Unit is going to be meter. Frequency is going to be number of cycles that they are passing one specific point in 1 second. For the black line, if you go here, black line, and you choose this one, only one, the frequency is going to be 1. If I move this one and put it there, okay, put it here this time, and you want to figure the frequency in this position for the black, black line is going to be 1 cycle until here, and that's going to be 2 cycles. So 2 cycles per 1 second. So the frequency is going to be 2 hertz or 1/s. Now we will switch to a discussion that we call it diffraction. We want to know what's the meaning of diffraction and how we're going to use the diffraction. Let's assume you have a wall, and that wall somewhere, it has a window, hole, or whatever. There is a place in it that, if you shoot something straight to that hole, it will pass. So if I throw particles to this way, this wall, okay, this is going to be wall, they will stop whenever they hit the wall, except if the particle is pointing exactly to the hole. In that case, it will pass. So again, this is particle. Okay. Now change this one. Okay. Change it to wave instead of particle and see what will happen. If you change it to wave, like just normal light, and repeat the experiment, and I'm going to show here, I'm going to show it by, show the light or any wave by this arrows. So we have wave this time. Okay. Again, all of them, they will be stopped by the wall, except those that they will reach, or they go straight through the hole. Okay, so if we have somewhere here, let's say we have wave that is pointing exactly to this hole, when it's trying to pass the hole, you will see that this light or this hole start to behave as a new source of light, and it will send the wave. It will send the wave in any direction, including the one that goes straight. So this new hole, it will behave as, I'm going to say, new source of light. Okay. This is kind of like part of nature of wave. And the funny thing, when you repeat the same experiment with 2 holes, you will see weird or really unique properties that they are belong only and only for stuff that they have a wave. So next experiment, what I'm gonna do, I'm gonna put 2 holes on the wall. Okay. I'll put 2 holes on the wall, and I will repeat this experiment. But before I do this experiment, before I repeat the experiment with 2 holes, I'm going to show you 2 things. One, we call it constructive interference, and the second, destructive interference. And then we will repeat this experiment, but with 2 holes. First one is going to be the constructive interference. What's a constructive interference? Let's say you have 2 waves. Okay. We have 2 waves. And the first wave, I'm going to show it here. Wave 1, we will show it by psi, and I call it 1. And this one, again, I call it wave 2. And I will show it by psi 2. Okay. If you add these 2 waves, if you add them, a product, okay, so I'm going to say, if you add them, what you will get new wave that is stronger than the original, stronger than any original wave. And I'm going to show here the product. I will write it down because I need more space. We say this one, wherever is positive or it has maximum point, that one almost it has positive or maximum point. When you add them, that area, it will be bigger. So we get new wave. This is the product, okay, or the new wave, and it's gonna have here this is bigger than the original, any original wave. Okay, what's the meaning of this? We call it amplitude. Okay, we call this one amplitude. This is going to be the intensity. And here we say amplitude or the intensity. Amplitude of first wave, this is amplitude of the second wave. Amplitude is the distance between the horizontal line and the maximum point. Okay. And if the amplitude is a bigger number, then you will see the light shine, or it has higher intensity. When you add 2 waves that they are in same phases, okay, in same phases, okay, in same phases. What do I mean by same phases? Whenever or wherever this one is pointing up or is maximum, that one also is maximum, or at least both of them are positive. They have same phases. Okay, at least both of them are positive. When you add them, the new one, okay, the new one is going to be equal to A1 plus A2. So the new amplitude or the intensity is going to be A1 plus A2. Your wave is going to be stronger. You build new wave with higher amplitude or intensity. We call this one constructive interference. Why? Because we build stronger wave. If you repeat the experiment, but same wave, okay, but this time you keep the first one here as it was, this one is A1, But when it comes to the second wave, second one, you flip it, okay, to make it out of phase. Whenever this one is positive, this one is going to be negative. It has negative phase. Now that one turned negative. Here we're going to make it positive. So A is going to be A2. That one is A2. And this one is A1. We say these two waves, sorry, wave 1 and wave 2, they are out of phases. Okay, out of phases. Because they are out of phases, if you add them, what you will get, it depends how much they are out of phases. Is it exactly out of phases? If they are out of phases, let's say when this one is maximum and is positive, that one is minimum, but negative, we say they are completely out of phases, and when you add them, you get nothing. Okay, you get nothing. You added two waves to each other, but you got nothing. There is no amplitude. There is no amplitude, or there is no intensity. So we say in this case we are dealing with darkness. It's like you are pointing to an object. You shoot two lights to that object. Both of them are, out of phases of each other. When they reach each other, they will cancel each other. So that object is not going to see any light from these two waves. In that case, we say we are dealing with distractive interference. So we call this one distractive interference. We got nothing. Okay. How about this? Okay. Let's say how about this? If I add them, what will happen? Okay. You find the amplitude. This is the amplitude, a distance between the horizontal line and the maximum point. That's the amplitude. I'm going to call this one A1, and I call this one A2. Check this too. Find this position on the second wave. Okay. Here is positive. This one is negative. So when you add them, they're going to cancel each other. Okay, they will cancel each other. And next, check here. This one is 0. Well, if I go straight, maybe close to the minimum. So I will get, I will get wave that is going to be positive at the beginning. It will be positive at the beginning, but then I'm going to show it by smaller amplitude. And then it will be negative. Let's call this one A prime and compare it with A1 and A2. We're going to say A1, or like A prime. A prime is supposed to be A1 plus A2. Okay. A prime is going to be smaller than A1 or A2. Why? Because they will cancel each other. Okay. So A1 prime, A1 or A2, they will be bigger than A prime. The new wave or the product a new wave. The new one is gonna be weaker than any original, wave, because they got cancel each other. To some extent, they cancel each other, but it's not 100%. So they were not completely out of phases. Okay, when they are completely out of phases, they will be 180 opposite of each other, like this. Maximum, minimum. Okay, 0, 0. Okay, 0, 0, and minimum, maximum. Okay, that one we say they are 180 out of phases, completely opposite of each other. So these two, they will cancel each other, and you're not going to see any new wave. Okay, we call them the distractive interference. We are destroying the amplitude. This is not a good thing to do. Now let's get back to experiment that we were supposed to do and deal with the constructive interference, constructive and distractive interference. So we said, let's repeat this experiment by putting or placing 2 holes on the wall. And we're gonna use here same wall, but this time with 2 holes, and repeat it with same source of light or waves. All these waves, they will be stopped except this one. And when it's reaching first hole, the hole start to emit the light in any direction, including the one that goes straight. And the second hole, if you shoot light to it, it will send the light again in any position, any direction. Okay. Now we will have some places that the red waves cross the black waves. Let's call the red, call them psi 1, and the black, we're gonna call them psi 2. Okay. And so if I track, for example, these waves, I can see cross here, there, and there. Okay. Or if you track the red one, this red crossed the black waves this position, and also here. Okay. Next thing that you need to do, put a sensor that it can record any waves. I can actually do it by using negative film. Remember the old cameras? Old cameras, we used to put film in it, back of the camera, but we were saying like, hey, do not open the film exposed to light, because if you do it, you're gonna burn the film and you will ruin the film. So don't do it when you are trying to work on the film. You have to do it in under red light at least. And so I'm gonna use that one, or you can put like a digital sensor here and see how much intensity or how much light is reaching. So I will put a plate or film here. So this is gonna be our detector. Okay. When you put the detector, you will see that this film, it will have some spots like this area. For example, we will see something, maybe there we will see, and then nothing, and you will see here something again, maybe there, and again you will see some something here. Okay. In this area, what's happened? Waves reach the film and did a chemical reaction on the film. Okay. Anytime lights reach film, it will, what it does actually, it will oxidize the film. And when it oxidizes the film, it will leave thread on the film. But in order to do it, we need to have energy. There must be light reaching the film, and then you can actually say you can have a thread on the film. So anywhere that you have line, that means something reached the film. In this area, we say we have constructive interference, or at least we have intensity. So if you don't want to say constructive interference, you'll like that one because maybe it's not really exactly constructive. We can say intensity is not equal to 0, or amplitude is not equal to 0. In this case, here in the white area, nothing reached the film. Because nothing reached the film, we can say we have diffractive, okay? Diffractive interference. Diffractive interference, that means amplitude is equal to 0. I'm talking about the white area. So here, amplitude is not equal to 0. We do have some intensity. In white area, amplitude is equal to 0. This behavior is unique and belongs to wave, okay? Only wave. Now, repeat this experiment by replacing the waves with electron and see what will happen. Okay. And remember, at the beginning of this lecture, we start with particles. And I said, if you start with particle and you shoot them to wall, you will be safe. Okay? You will be safe if you are standing here, anywhere back of this wall. But if you are in the front of this hole, then you will see something is coming to your side. If you replace this experiment, if you repeat this experiment, but this time replace the particle by waves, it doesn't matter where you are standing. If you are standing here, there, or this area, you're gonna see sunlight. Intensity, maybe it can go up and down, but you will see sunlight. We said if you are there or here and you are dealing with particle, you should not see anything. And in this case, when we have wave, we're not going to see anything. But if I stay here, still I'm not in the front of the hole. I can see some light. Light maybe is not a strong one. If I'm here, again, I can see something coming out of this hole. But like we said, if you replace it by here, if you replace it by particle, you will be safe and you're not gonna see anything. So now I'm gonna choose electron, and electron is a particle, okay, because it has mass. And at the beginning of the semester, chapter 2, we calculate mass of electron, and we said mass of electron is 2,000 times smaller than mass of proton. Okay, so we're talking about particle. Electron is a particle from chapter 2. Okay. From chapter 2, we know electron is a particle. So we expect this behavior for electron. Let's repeat the experiment. And let's repeat the experiment by using electron and see what will happen. And I'm going to use two holes and see what will happen. When you use electron, the electron is a particle, so I'm shooting electron. The wall Also, I will shoot the hole. I expect that if I'm here, I will be safe. This position or that one. So 1, 2, 3, we will be safe. We're not going to feel anything. And I expect this one, it will go straight. Same thing here. I expect the electron to go straight. But reality, when we put a film, again, a film or detector in the front of this, in front of this, like say wall, we saw not only in these two places, we have something, okay? We have a thread on the film. We got some stuff there, maybe here or there. Okay. And this, this result cannot be answered by particles because based on this design, I should expect only this thread and that one. Why? Because they are straight in the front of the first and second hole. Now the question is going to be, how did we get 1, 2, and 3 lines? You can answer those, you can find, answer for those 3 spots only and only if you assume electron is a particle. That's true, but also sometimes it will behave like a wave. Okay, electron is a particle. Electron is a particle, but sometimes it will behave like a wave. It's a particle, so it's supposed to be stopped by wall. If it's pointing in front and it's pointing to the hole, it will go straight. Nothing can stop it. But also, if you treat the electron as a wave, you will have diffraction. Okay, you will have diffraction. And now it depends how many holes you have. If you have 2 of them, any electron, when it's passing this hole, it will behave as a wave, and it will, like a wave of that electron, it will do interaction, or it will do some interference with wave of other electrons, and you will see this pattern for them. Okay, so the reason we see this pattern for electrons is just because electron, it has dual nature. It can be wave and particle. Okay, so it has dual natures, wave and particle. Do we know when it's going to be particle and when it's going to be wave? No idea. We don't know that part. Okay, because we don't know it, we're going to deal with some problems, and we will talk about it at the end of this chapter. So for now, accept this one from me, that electron, it will behave as a wave, as a particle sometime, and so you can treat it as a mass. You can shoot some somewhere with electron, and you can eject actually something from that surface, and we use it in chemistry. We use that technique a lot. We have some stuff, we call them electron gun. We shoot electron to a surface to generate wave, like x-ray wave. That's the way actually we generate the x-ray. Next thing is we can treat it as a wave. If it's a wave, then you should expect this diffraction pattern for it. Sometime here, like in that area, you see thread, because you see thread is gonna it's gonna ruin, or it's gonna leave a thread on on the detector. It's gonna do a chemical reaction with the detector, and you will see white spot on the detector. Okay, So now I will be talking about here relationship between wavelength and the frequency. We have C equal to lambda multiply frequency. Okay. C equal to lambda multiply and frequency. What's the C? C is velocity of light, okay, or speed of light. And it's equal to 3.00 multiplied 10 to the power of 8 meter over second. So unit of C is going to be meter over second. Unit of wavelength will be meter, and unit of frequency has to be 1 over second. So meter multiply 1 over second is going to give you, it will give you a meter over second. Okay. Example, find frequency of light or wavelength that is equal to 202 nanometer. So we want to find wavelength, frequency for a light or wave. For a wave that is that it has wavelength is equal to 202 nanometer, and you know C is equal to 3.00 multiplied 10 to the power of 8 meter over second. Okay. And you're going to use this formula that C is equal to lambda multiplied frequency. So frequency is going to be C over lambda. The final answer, it will have unit of 1 over second. Till now, I cannot use this unit, because if I use this unit, I cannot cancel the meter by nanometer. So the final answer is not going to be 1 over second, and I need to fix that problem. So I go with this. I have wavelength equal to 202 nanometer, and I'm going to say 1 nanometer is equal to 1 multiplied 10 to the power of minus 9 meter. So wavelength, it will be 202 nanometer multiply 1 nanometer is equal to 1 multiplied 10 to the power of minus 9 meter. We cross nanometer by nanometer, and the final answer is going to be 2.202 multiplied 10 to the power of minus 9, or 2.02 multiplied 10 to the power of minus 7 meter. Okay. And C is equal to 3.00 multiplied 10 to the power of 8 meter over second. So now let's calculate the frequency. Frequency is going to be 3.00 multiplied 10 to the power of 8 meter over second, divided by wavelength 2.02 multiplied 10 to the power of minus 7 meter. Now I can cross meter by meter, and I will get the final answer in 1 over second. So I go 3 multiplied 10 to the power of 8 divided by 2.02 to the power of multiply 10 to the power of minus 7. I got the final answer. Final answer is equal to 1.49 multiplied 10 to the power of 15 unit 1 over second or hertz. 1 over second or hertz. So again, I had to transfer the unit of nanometer to meter, because I have the C in meter over second. I cannot cross the nano by meter. I need them to be the same unit. And that's the reason I transfer the nano to meter first, and then I use the wavelength. Another formula that you will be dealing with will be energy is equal to h nu. Nu is the frequency, and h is the Planck constant. Okay. And E is energy. Okay. H is equal to 6.626 multiplied 10 to the power of minus 34, and unit is joule to second. Joule to second. Frequency, we said 1 over second. So if you go with here, energy is equal to H. It has unit of joule to second. Frequency 1 over second. You cross second by second, you will get joule, which is the right unit for energy. Energy, it can be in joule or kilojoule. Okay. How did we get this formula? Planck came with this formula, and he said, let's assume, okay, here. Okay. Here we have energy. Okay. He said, the classic physics, it says, if you give any energy to any molecule, it will be taken by that molecule or that system until you stop source of the energy. When you stop source of the energy, it will give you back exactly same amount of energy, wave or energy that you gave it. Okay. He said that's not true. Okay, that's not true. And they did the test with the they call it, black body. And you take an object, you hit the object. When you hit the object, it will get red, and then it will get maybe orange, and then slowly it will move to, white, and I think at the end it will be kind of bluish. And if you stop hitting that object, you expect, to get all wavelength or all frequency from that, hot object. But then when they put a detector in the front of it, they saw they're not getting exactly all the energies or all the waves that they give to this, to the object. They see only unique, numbers and or specific numbers of energy. And from that, time, he said this is not true to say that if we hit object, we'll take any energy. That's not going to be true. Planck, he said, if you treat this one as a baseline, okay, so, and this is going to be the room temperature, okay, room temperature. In room temperature, all molecules or atoms, they are taking first level of energy, okay, first level of energy. And now, if you give it energy, they go to a higher level. Let's say n equal 2, then n equal 3, n equal 4, n equal 5. Okay, so he said, when you give energy to any system, okay, energy must be enough to take the electron or the system and shoot it to next level. So energy has to be equal this gap, okay? Equal this gap. Otherwise, it will not be, it will not be reserved by the system, okay? So the energy has to be equal to this. And how much is this energy? Is equal to h nu. What will happen if I give it energy equal to this? Okay, that amount of energy. A system or the molecule, it will not take entire of this energy. What it does, it will relax. Okay, so the system, we shoot it, okay, I'm going to show it here. We shoot it to higher level, we shoot it here. It's going to release this amount of energy. This one, it will give it as a heat, vibration, or any things. It will give it to outside, and it will get back to here. Okay. So that part, it will be emitted, and we will see it. Okay. We will see the temperature of the solution went up, or we see sometimes we see light is coming out of the system. Okay. If I send it to higher and I hit, that level, then I will say it's gonna stay there until I keep hitting it. But the second I stop, it will go back. You cannot expect that this system, it will take energy that is not equal a gap between these levels of energy. Energy here that is equal to h nu, we call it quantum of energy, and n for now we call it number of quanta. Later on I will call it level of energy. So he's saying, Planck is saying that if you start with n equal 1 and you shoot the electron, or like in a system, you shoot it to higher level, let's say to, like here, n2, if you give it that amount of energy and energy is equal to h nu, it will be taken by the system. Okay, it will be taken by the system, that's fine. If you give it 2 times of this, okay, so they call it E1 here. This one is going to be 2 times of h nu, okay, 2 times of the gap between this level first and the second level. Energy that you need to spend to send it to the third level is going to be 2 times of this, so it's going to be 2 multiply h nu. And if you give it energy equal to this number, okay, system, it will release this amount of energy. So this amount of energy, it will be emitted. We'll have emission. Okay. And rest. Now the system, it will get back to this one. And from now, okay, if we stop source of heat or source of light, then system, it will get back. But that one, okay, you can see it as light or sometimes as heat. Okay. So for now, we said the gap between 2 levels of energy, we call it quantum of energy. And you can, you can expect from any system to accept only and only that amount of energy, the h nu energy from, whatever you say you shoot to it. Okay, if you give it higher, let's say 1.5, it's not going to be taken. The half, it will be tossed, it will be emitted, and the rest, it will be taken. Okay. And now I'm going to go through another example. I have wavelength that's equal to 315 nanometer. Okay, 315 nanometer, and I'm trying to find energy and frequency, energy and frequency of this, wave. Okay, so first thing, I'm gonna say C equal to lambda multiply frequency. Frequency is going to be equal to C over lambda. C, it will be in meter over second. Lambda must be in meter. So then I can cross meter by meter and I get 1 over second. We need to fix wavelength. We go wavelength equal to 315 nanometer. Transfer nanometer to meter. 1 nanometer is equal to 1 multiplied 10 to the power of minus 9 meter. So you cross nano by nano. We will get 3.15 multiplied 10 to the power of minus 7 meter. So now frequency, it will be C over lambda. C is the velocity of light. Meter over second, divide by wavelength. You cancel meter by meter and you will get 1 over second. Answer for it, I go with 3 multiplied 10 to the power of 8, divide by 3.15, multiply 10 to the power of minus 7. I got this one equal to 9.52 multiply 10 to the power of 14, 1 over second, or hertz. Okay, 1 over second or hertz. So now we got the frequency. You want to calculate the energy. You have two options. Okay, so first option for energy, we can go energy is equal to h nu, or we have the frequency, and instead of frequency we can say we have the formula of h nu, and we know also frequency is equal to C over lambda. If we mix them, we will get energy is equal to h C over lambda. Okay, so we have two formulas to calculate energy. Okay, so I had the first formula was h nu, and the second formula I said I have C equal to lambda multiply frequency. Frequency is equal to C over lambda. And I said if you merge them, you get energy is equal to h multiply C over lambda. It will give you hc over lambda. Okay, let's call this one 1 and call this one 2. Okay, what's the difference between 1 and 2? Nothing. Only difference that you might see it as a difference. When you use this formula to calculate energy, the only thing that you are dealing with is h, which is 6.626 multiplied 10 to the power of minus 34 joule to second. This is a constant number, and a frequency, you had to calculate a frequency from first step, and it was equal to 9.52 multiplied 10 to the power of plus 14, 1 over second. So I had to calculate this one. Okay. If I put it in this formula, and by chance my frequency is wrong, energy is going to be wrong. Okay. I had to calculate the frequency, and if I put it in a formula and the frequency is wrong, energy is going to be wrong. Nice thing with this formula, hc over lambda, both c and h, both c and h are constant. Both c and h are constant. So that means numerator, in this case, numerator is constant. The only thing that's you're going to use is going to be the denominator. And denominator is given. The question gave it to you. You had to transfer the unit from nano to meter. So the only thing that you did, you transfer nano from nano to meter. And I can say in this case, there is less chance to make a mistake than the first one. Again, if you really follow the, follow the math and do it perfectly, and by using, the frequency and fit this formula, you're gonna get the final answer, and there will be nothing wrong with using first formula. And I'm gonna show it to you right now. So I go with energy is equal to H nu, H 6.626 multiply 10 to the power of minus 34 joule to second multiply frequency 9.52 multiply 10 to the power of 14, 1 over second. You cancel second by second and you will get the energy. So I will write the energy for it. Next one is E is equal to hc over lambda. H is 6.626 multiply 10 to the power of minus 34. And it's going to be joule to second multiply C meter over second divide by lambda, and we have the lambda equal to 3.15 multiply 10 to the power of minus 7 meters. Okay. Cancel meter by meter, second by second, it will give me joule. Okay. And let's write the energy. Okay. So now I'm going to write the answer for first part. It says 6.626 power of minus 34 multiply 9.52 to the power of 14. I got this one equal to 6.31 multiply 10 to the power of minus 19, and unit is joule. Okay, let me double check it. 6.626 of minus 34 multiply 9.52 to the power of 14, 6.31 multiply 10 to the power of minus 19. Next one, we go with 6.626 to the power of minus 34 multiply velocity of light divide by wavelength, and gave me 6.31 multiplied 10 to the power of minus 19. Okay, minus 19. So again, it doesn't matter which method you are using, whether you are going with E equal to H nu or E equal to HC over lambda, you will get the same answer. Okay. Just be careful about, the using the calculator when it comes to the second formula. Okay. And I'm gonna talk about, a problem with, using the calculator. Okay. Let's say you want to do this math. You want to say E equal to HC over lambda. Okay. And you said Okay, I have the H, and I'm gonna multiply it by C. So till now, there is nothing wrong. The problem is going to be when you divide it by wavelength. Okay, so this one is going to give you, the answer for the numerator. That's fine. Now you want to divide it by wavelength. Okay, now you say energy is equal to, I have 6.626 or multiply. So till now we have 1.99 multiply 10 to the power of minus 25, and you want to divide it by wavelength, and wavelength was 3.15. we said, I believe 3.15 multiply 10 to the power of minus 7. Okay, if you just simply write this number and then you divide it by this denominator, in reality your calculator is going to do this calculation. It's going to say E is equal to 1.99 multiply 10 to the power of minus 25 divide by 3.15 multiply 10 to the power of minus 7. Okay, because you did not tell the calculator that take the numerator and divide it by entire the denominator. You did not tell the calculator. So whenever you want to do this calculation, please put the denominator inside the brackets or parentheses. Okay, do it. If you don't do it, it's going to do this calculation, and this is wrong. This is the correct one. So please be careful about using your calculator, otherwise your answer is going to be off by 10 to the power of 7. Okay, so now that we know how to calculate energy and also wavelength, we'll go a bit deeper with the chapter, and I'm gonna go through stuff like orbital. So here, if you take like a source of light and put something in front of like this glass in front of it. It depends how you keep the glass in it. You can actually spray. You can like separate a wave that's coming from this source of light. So we have bunch of them. Okay, we can separate them, and they can be completely different energies or different wavelengths or frequencies. So let's say here frequency 1, frequency 2, frequency 3. We can use some techniques to separate them. And when you put detector or film in front of them, you will see that here you left a thread, one there, that's a second thread, and third and fourth one. Okay. And I remember in Boston, we used to do this experiment. We give unknown sample to students, and we gave them like a detector, and based on position of these electrons and also their energies, we asked the student to calculate the wavelength and also figure the source of the light and see whether it's like, for example, hydrogen, neon, or something else. But the question is, what's the science behind it? Okay. And Niels Bohr came with this fact that he said, any atom that you pick, it has nucleus, and nucleus is the place that we have protons in it. Around that nucleus we have orbit. Okay, sorry about this one. We have orbit. So, and first orbit, we show it by n equal 1. And second orbit, we show it by n equal 2. Electrons are hanging in this orbit. And based on their distance from the nucleus, what's the distance from the nucleus, energy will go up and down. Energy for any electron, you can calculate through this formula. Energy is equal to minus RH multiply 1 over square of n. Okay, and I'm going to say here I call that one I. Okay. I, you can give it any number like 1, 2, 3, and go up. So n can be 1, 2, 3, and up. N cannot be 0, because if n is equal to 0, that means we are dealing with nucleus. So if you want to calculate energy of electron for first level when n is equal to 1, it's going to be equal to minus RH, a constant number, multiply 1 over 1 divide by square of n. What's the n for first level? It's going to be 1. 1 to the second is going to be 1. So energy for n equal 1 is going to be equal to minus RH. How about n equal 2? For n equal 2, energy is going to be equal to minus RH multiply 1 divided by square of n, and n is 2. So it will be minus RH 1, it will be 2 to the second. It's going to be minus RH divided by 4. RH divided by 4. So we got, here we got the energy for first level equal to minus RH, and energy for the second level, we got it minus RH divided by 4. Now, what's the RH? RH is a constant number, and we call it Rydberg constant number. So RH is a constant number, and it's equal to 2.18 multiply 10 to the power of minus 18 joule. Again, this is a constant number. Now the question is going to be, what will happen if you send one electron from first level to second level? How much change in energy happen? And I'm going to go through this one in the next lecture. So I'm going to stop the lecture here, and thank you guys.